Hello, welcome to Lecture 4. We're going to start this lecture exactly where we left off in Lecture 3, which is saying, what if we have a long, heavy rope and we start a wave going up the rope? What happens to the wave speed? Does it get bigger, does it get smaller, or does it stay the same? Hopefully you had a chance to think about that and you committed yourself to an answer and wrote it down. We'll go through that problem on the next slide. So we have here a long heavy rope hanging from a ceiling. Let's say that our rope has mass m. Let's use a capital M for the mass of the rope. We generate a pulse, that means we start a wave at the bottom of the rope and it travels upwards. What happens to the speed of the wave on the rope and why? So let's remember what we know about speed of wave on a string. We know that the speed of a wave on a string is the square root of the tension divided by the mass per unit length. So F equals tension. Mu equals the mass per unit length. That's the mass of the rope divided by the length of the rope. We know that guy is a constant. So this tells us that the speed of the wave on that rope is proportional to the square root of the tension. If we can sort out what happens to the tension, then we can figure out what happens to the wave speed. Let's look at 3 different spots and ask about the tension in each of those 3 spots. What about the tension at the bottom? What about the tension at the middle? And what about the tension at the top? Okay, let's do the bottom first. If we were to draw the free body diagram, we would have the force due to gravity, or the weight, down. We would have the tension up. I'll use F for tension. Well, what's the force due to gravity at the bottom? There's absolutely nothing below it, so the force due to gravity has to be 0. Our Newton's second law says the sum of the forces, and I'll put a B on here for at the bottom, says the sum of the forces equals 0. If there's no weight, then there's no tension. Those 2 guys have to be 0. Okay, what about at the middle of the rope? We'll change colors for the middle. At the middle of the rope, we can draw the same free body diagram. We've got the force of gravity down. We've got the force of tension at the middle. The force due to gravity would be the mass at the middle times g. The mass at the middle is everything that's below the middle of the rope. That's half the total mass of the rope. Okay, so my tension at the middle is equal to 1/2 the mass of the rope times g. So we see the tension in the middle is bigger than the tension at the bottom. Okay, last part we'll look at. What about at the top of the rope? Let's do our free body diagram. We have the force due to gravity that points down, the tension in the rope at the top that points up. The force due to the gravity is the weight of everything below that point. That's the entire rope. So mass at the top times g, which is the whole rope times g. The sum of the forces has to be 0, so the tension at the top is the whole mass times g. So what we see is that as we go up the rope, tension increases because the mass increases. So as the wave moves up, Fg increases, which means that tension increases. And if the tension increases, the wave speed also increases. So that's the answer to the question, what happens to the wave speed? It gets faster. The reason it gets faster is because the tension has to equal the weight, and the weight gets bigger the further up the rope we are, therefore the tension gets bigger, therefore the speed gets bigger. In this example, we have a long rope. It's 80 meters long, and the mass of the rope is 2 kilograms. Why don't we make a list as we go? So the mass of the rope, I'm going to give that a little m. That's 2 kilograms. And the length of the rope, I'll call that capital L, is 80 meters. There's for our rope. The rope is stretch taut by a 200 kilogram box of rock samples attached at the bottom. So at the very bottom, so down here at the bottom, we have some rock samples, and the mass of those rock samples is 200 kilograms. Part A, the geologist at the bottom of the shaft jerks the rope sideways, so he's making a wave on the rope. What is the speed of the wave on a rope? So we know that the speed is the square root of the tension over the mass per unit length. Let's make sure we know what to do with everything here. Our previous conceptual example talked about the influence of the mass of the rope, so let's discuss that first. In our problem, we have that the mass of the rope is 2 kilograms. That's a lot smaller than the mass of the rocks tied to the bottom. That means we're going to neglect the effect of the mass of the rope on the wave speed. Since the mass of the rope is only about 1% of the total mass overall, that's a fairly good assumption. So we're going to assume that wave speed stays constant all the way up. Okay, so let's ask, what does mu stand for? Mu is the mass per unit length of the rope. So that's the mass of the rope, 2 kilograms, divided by the length of the rope, 80 meters. So our mass per unit length of that string is 0.025 kilograms per meter. Okay, what about the tension in the rope? Well, let's have a look at our box of rocks at the bottom. Let's draw the free body diagram on our box of rocks. We have the force due to gravity, or the weight, pulling down on the box, and we have the string pulling up. That string force is a tension force. So we'll write Newton's second law. Sum of the forces in the y direction is the mass times the acceleration in the y. We have the tension holding it up. Subtract the weight pulling it down, equals 0 because the box is not moving up or down. So the tension is equal to the weight, which is going to be the mass of the rocks times g, 200 kilograms, times 9.81 meters per second squared. That gives us a total tension force of 1,962 newtons. You can round that to 1,960 if you wish to keep 3 sig figs. So now we're all set to find our wave speed. We'll put in the tension, 1962 newtons, divide that by the mass per unit length, 0.025 kilograms per meter. Take the square root of the whole thing and we get the wave speed, and that turns out to be 280 meters per second. That wave goes pretty fast up that string. Part B of this problem now asks, how many cycles of the wave are there in the rope's length? So the geologist shakes the rope and it makes a wave travel up the string. Maybe it looks something like that. What we're trying to figure out is how many wavelengths. So how many cycles could also say how many wavelengths. So if we want to know how many wavelengths, let's find out the wavelength of the produced wave. We know V equals F lambda, which means lambda equals V over F. V is 280 meters per second, divided by the given frequency of 2 hertz. Tells us that the wavelength of the wave that geologist sends up the rope is equal to 140 meters. That's a pretty big wavelength. Okay, so how many wavelengths exist on the string? So the number will be the number of cycles, or the number of wavelengths, will be the total length of the string divided by a wavelength. The total length of the string is 80 meters. Oops, that 0 looks an awful lot like an 8. I'll just fix that. 80 meters divided by 140 meters equals 0.571. So there's just over a half of a wavelength on that rope. I'm going to leave this question as a homework question. I'm not going to make a video for it, but I will post the solutions, and I'm going to give you a hint before I leave you to it. So we have 2 wires. One of them is steel and the other is copper, so we already know they're a little different. We know the diameters of the wire, so 1.25 and 1, and we know the tension in the wire. Seems like there's some things we don't know though. We don't know the mass of the wire and we don't know the mass per unit length. We're asked to find which wave will travel the length of the wire the fastest. So this problem is asking us to figure out something about time. If we want to figure out something about time, one equation we're probably going to use is V equals distance over time because we know the length of the wires. If we know the length and the speeds, we could figure out the times. The other thing we know about the speed of a wave on a wire is that it's equal to the tension over the mass per unit length, where mu is the mass per unit length is m over L. This poses a little bit of a problem because while we do know the length, we don't know the mass of the wire. Let me give you a hint as to how you can deal with that. Let's think about mu equal to mass per unit length. The first thing we can think about is what is mass m? Well, one equation we could use is that density, normal density, kilograms per meters cubed, is mass divided by volume. And we do know the densities of copper and steel. Those are given. So that's kind of a hint that you could use to go here. So I'm going to say that mass then is density times volume divided by length. My symbol for density is the Greek letter rho. Kind of looks like a stretched out E or a curly lowercase p. So that's the Greek letter rho. Okay, next bit to deal with is V for volume. So let's think about our wire. A wire really looks like a cylinder. So a wire is a cylinder. We know the equation for the volume of a cylinder. It's pi times r squared times the length. In this problem, we don't know the radius, but we do know the diameter, so it'll be pretty easy to find the radius. It's just half the diameter. So I'm going to fill that in for my volume. Now I notice that I have length on top and length on the bottom, so they cancel. So my expression for mu then is density times pi times r squared. So this gives me an alternate expression for my V. So mu is mass over length, and mu is density times pi r squared. That means my wave speed is tension over mu, F for tension. Sometimes I forget and make it a T. Just fix that up. And V equals tension over rho times pi r squared. This gives you an alternate form when you know the diameter or the radius and the density for if you don't know the mass and the length. So with this hint, you should be able to go ahead and solve this problem, and then you can come back and check your answers against what I post.